The first problem on Lab 4 is beyond the numbers 3.30 Exhibit 1, which is on page 321 in the workbook. If you look in the workbook, it looks like a one-sample hypothesis test, but really it's a two-sample test. That 0.0728 in the workbook is really a sample proportion, so this really should be done as a two-sample test. In other words, do it the way it says to do it on the lab worksheet, not the way it says in the workbook. This problem is worth 2.5 points, 2 for Part A, which is the R stuff, and then half a point for Part B, the decision about the null, which would just be either that you're going to reject the null or that you're not going to reject the null. But Part A, the part about R, the code should be just one line because you're using the prop.test function. So you're going to use that, and then the first argument, you have to use the combiner, the C, to put the two numerators together. The second argument uses the combiner to put the two denominators together. Then you have to specify the alternative, well, the inequality that's in the alternative, and then you have to turn the Yates continuity correction off. That's basically it. If you follow along with the examples from when we did this in class, this one ought to be really quick because really it's just one line when you're using R. There's only one line of stuff that you have to type in. Problem number 2 is a confidence interval for a difference in means, where all the sample data is in that paragraph. Part A, whether the data are paired or independent, that's half a point. I guess really that's a one-word answer. Part B, computing the standard error, which would be based on your answer to Part A, that's where most of the algebra is going to be, so that's 1 point. Part C, you have to use stat key to get the critical value. I suppose you could use R if you wanted to, there's nothing wrong with that, but I figure stat key is going to be a little more conventional. So this is a confidence interval for a difference in means. You're going to use the t-distribution. Just copy that over once you've got the critical value all set up that you're going to use to get the confidence interval. Then Part D is really just algebra, because once you have the standard error and the critical value, then really you just have to get the point estimate, but that's not really going to be too bad based on what's up there in that initial paragraph. And then you'll get the endpoints of the interval pretty quick. And then Part E, is it reasonable to conclude that there's a difference? Once you have the interval, that's basically a yes or a no, and then the why or why not is based on what your interval is and essentially where 0 is, whether 0 is inside the interval or not. Problem number 3 is using R again, this time for a hypothesis test for a difference in means. So you're going to use the t.test function. You do have to import the data. So the grandstrand.csv file, that's where it is. You've got one sample in the first column, the other sample in the second column. And if you look at the point distribution, half a point is for Part B, just like it was before, and there was a make a decision about the null type part of a question. It's either that you reject the null or you don't reject the null. So Part A is worth 3.5 points. 1.5 of that is essentially for getting the data into R and getting it separated out. So half a point for the read.csv function, then half a point for storing each of the samples, and that would add up to 1.5 total. Then the other 2 points is the t.test function itself. Getting the sample data in there, getting the right inequality, and then having the output. The t.test function really only has to have 3 arguments. First sample, second sample, inequality. Although, considering what inequality it is, you could leave it out because it's the default inequality. So you actually could get away with 2 arguments here if you really wanted to. Problem number 4 on Lab 4 is a chi-squared goodness of fit test. And the hypotheses are already set up. If you look at the null, there is that model there of 50% going straight, 25% turning left, and 25% turning right. That's what the city traffic engineer thinks. And we want to see if there's evidence that the city traffic engineer's belief is wrong. Since the hypotheses are already set up, the first thing to do is get the expected cell frequencies. That won't be too bad, considering that we have those percentages in the null hypothesis. And yes, you do need the sample size, but it's not going to be that hard to get. You just have to add those 3 numbers up that are in the observed cell frequencies and you'll get it. Once you get the expected cell frequencies, the next thing is to determine the test statistic, where the way that the chi-squared test statistic is set up, you'll get a component of the sum from each category. Since there are only 3 categories, there are just going to be 3 components. So for each of those, so again, going straight, turning left, and turning right, you're going to have the observed frequency minus the expected frequency quantity squared divided by the expected frequency. Since there are only 3 categories, it won't take a ton of time to get that test statistic. Once you have the test statistic, you can compute the p-value using stat key. And since this is a chi-squared test, you want to use the chi-squared distribution, and then you just want to make sure you're using a right tail to get the p-value and that the test statistic is your cutoff. So what I mean by what's there in part C is if you go to stat key, you want this right here, the chi-square distribution. You get prompted for a value for the degrees of freedom. I'm going to put in things here that are intentionally not the right answer for the lab. That's definitely wrong, 8 degrees of freedom, but you would put in whatever your degrees of freedom is, then okay, and then right tail, and then let's say hypothetically my test statistic was 10.5. I would put that in as the cutoff. And then in this case, with 8 degrees of freedom and a test statistic of 10.5, you get a p-value of 0.232. What you get for your p-value screenshot will basically look like this. I think because the degrees of freedom that you'll have is so small that your chi-square distribution itself will look a little more severe. I don't think you'll get a nice hump up toward the top like that. And I think you'll have a more severe shape where it's more skewed, where more of it is the right tail. But that's basically the idea. Then the last part, part D, that's just another one where it's can we reject the null or not? So that one is worth half a point, just like that sort of question is in the other parts of this lab.